Hello everyone, welcome back to Diksha Karnataka YouTube channel, and you are watching Sankalp KCET 2026. And so far we have completed how many chapters? 6, 7, I think 6 chapters we have completed. So today's class I am not going to teach anything new, right? So what we are going to do, we are going to revise all the formulas in all the chapters that we have learned so far. So you can consider this video to be a quick recap plus all the important concepts at one go. So all the 6 chapter summary in one shot, right? So this will be very interesting and important video for all those who have missed the previous chapter. So if you watch this video, all the basic concept level and what are all the important formulas etc., that will be cleared, but in the in-depth concepts and in-depth for clarification, for that you have to watch my full-length videos. So if you have not watched them, you can check them out at a later time, but right now it's time for us to revise all the chapters one by one. So we will revise the chapters one by one, and if you want to download the note of this lecture as well as all the lectures that I have done, for that you have to join our WhatsApp channel. And if you are watching this video for the first time, then don't forget to click on the subscribe button below. Now let's start with the first chapter, electric charges and fields. It is the first chapter, and we will start with the first law that we have learned was Coulomb's law, and as well as the concept of electric field. So Coulomb's law was very important. So what is the basic form of Coulomb's law? Basic form of Coulomb's law is K Q1 Q2 divided by R square. Right, it is K Q1 Q2 divided by R square. This sign signifies we are only taking the magnitude. This is the magnitude of the force. Sign can be positive or negative depending upon whether it is a repulsive force or attractive force. So in some cases, in any case, if you find the force to be negative, that means it is an attractive force. For negative force, it signifies attractive force. Positive force signifies repulsive force. Okay, now this K is called Coulomb's constant. This K is called Coulomb constant. Very important value to remember. In mathematically it is 1 by 4 pi epsilon naught, and numerically the value can be approximated to be 9 into 10 to the power of 9. Very easy to remember, 9 10 to the power of 9, right? And unit is Newton meter square per Coulomb square, and this constant epsilon naught is called free space permittivity. Free space permittivity, its value approximately 8.854 into 10 to the power of minus 12. In some cases, in some numerical cases, you can even approximate this value to be 9 into 10 to the power of minus 12. But there is a risk. Some student often mistook this epsilon naught for K and put the value 9 into 10 to the power of 9. So don't do that. Be careful. This is epsilon naught, which is much smaller than this K. Okay, it is 10 to the power of minus 12. So remember this value. For approximated answers you can use 9 as well, but this is the exact value, not exact value but very close to the exact value. For medium of dielectric constant K, this formula is valid when you are keeping it in free space. So if this entire arrangement is kept in free space, that is in vacuum, no medium is there, then this formula is valid. But if you put this same charges in some media, because the medium we are living on Earth, so around Earth there are a lot of different mediums. Air is one of them. Now free space and air are almost same, but if you are using water, say, or any other medium, say any other dielectric medium, say mica, there are a lot of different mediums available, oil, petrol, etc., right? For that, if we have something called dielectric constant. Okay, dielectric constant is defined by this, the permittivity of the medium divided by permittivity of that particular, permittivity of the medium divided by permittivity of free space. So this is how you can define dielectric constant. Sometimes it is also called relative permittivity. Okay, relative permittivity, the same thing, dielectric constant, relative permittivity are same. Permittivity on the other hand, permittivity of a particular medium is different value, but we are not super interested in the permittivity of a medium, but we are mostly interested in dielectric constant and relative permittivity. Okay, so you can write permittivity in terms of dielectric constant as this. Okay, so this is one important formula to remember. So dielectric constant, if dielectric constant is K, then effective distance in vacuum will be R root K. So if instead of having this in free space, if you put it in water, if you put the arrangement in water, only thing that you need to change is change this value of R to R root K. Okay, everything else will be same. Everything else will be same, only the distance will be changed to R root K. There are some complicated problem based on this concept for JEE students, but we are not going to discuss. This is a KCET class, so our focus mainly on KCET, right? The electric field on the other hand is defined for a single charge. Okay, if there is only one charge, what will be the effect of that charge at some unknown location, at some distance? Okay, there are no charges present, so will there be any effect present? Yes, there will be an effect present, and that is defined by electric field, and its formula is 1 by 4 pi epsilon naught q by r square. R cap, again it's a vector quantity. Okay, so R cap depends on the the nature of the charge. If it is positive, then R cap is away. If it is negative, then R cap is towards the charge. Okay, that's how you can even find the electric field. Now there is a close relationship between electric field and force. There is a very close relationship between electric field and force. So suppose I have an existing electric field, for example electric field around earth. There are some cases where electric field around earth is present. Now if you put a charge near earth, then what force it will experience? It will experience a force that is force times the electric field, which is very, very important to remember. Now let's move on to the next part, electric dipole. Electric dipole is also very, very important concept. Electric dipole moment is the product of magnitude of one of the charges and distance between them. It is a vector quantity. So dipole moment is the most important quantity, which basically gives you that magnitude of any one of the charges times the distance between the charges. And by the way, what is an electric dipole? Electric dipole is two equal and opposite charges separated by a very small distance. The distance has to be very, very small. Now P is equal to Q into 2a n cap. N cap is a unit vector from negative to positive charge. So basically n cap is a unit positive vector which is from negative to positive charge. So the direction of dipole moment is from negative to positive charge, right? So the dipole moment is something which points from negative to positive charge. Be careful, in chemistry it is opposite, but in physics it is from negative to positive. Now dipole, in terms of dipole there are few terms that you need to remember. Electric field on the axis of a dipole, electric field on the axis of a dipole is given by 1 by 4 pi epsilon naught 2p vector divided by r cube. So as you can see, electric field normally varies as 1 upon r square, but for dipole it is 1 upon r cube. Okay, here the dipole moment is already defined. For points on the equilateral plane, for equilateral plane it is given by minus 1 by 4 pi epsilon naught p by r cube. Again the variation with r is same. The variation with r is same, but you can see that electric field and dipole moment are in the same direction here, whereas electric field and dipole moment are in the opposite direction for equatorial plane. Okay, now torque acting on a dipole. So if you keep a dipole in an external electric field, it will experience a torque, right? So already existing electric field is there. Okay, and if you keep a dipole, it will experience a torque. What is the meaning of torque? Torque means it will try to rotate. It will try to rotate in this electric field. Okay, and that torque is basically given by PE sin theta. Now potential energy, when you keep that inside this electric field, the potential energy of the system will be minus Pe. Sorry, there will be a negative sign, minus Pe cos theta. Minus Pe cos theta is the potential energy of the dipole. Now Gauss's law. So electric flux through a closed surface S is given by phi equals to Q by epsilon naught. Now phi is defined as E dot ds close integral. So therefore E dot ds close integral is given by Q by epsilon naught. Here Q is the total charge enclosed by the surface S. So suppose we have a closed surface, and within that surface if we have a charge Q, then what is the electric flux which is coming out of the surface? So for that we generally use Gauss's law. There are few properties of Gauss's law as well, few conditions attached to it. Okay, for detailed video, obviously we are doing only the recap. So if you want a detailed video, you have to check the complete chapter video. I have done it in 3 parts, so that's why it is a very huge chapter. So I am just giving you the summary of the chapter. Next is Gauss's law application. So electric field due to a long straight uniformly charged wire is given by 1 by 4 pi epsilon naught 2 lambda by r. What is lambda? Lambda is the line charge density, and as you can see here, electric field is proportional to 1 upon r. Right, electric field is proportional to 1 upon r. Field due to an uniformly charged infinite sheet is given by sigma by 2 epsilon naught, and not only that, it is basically a constant. As you can see, infinite sheet, charge sheet, the electric field will be constant. Sigma is the surface charge density, lambda is the line charge density. Electric field due to a uniformly charged thin spherical shell. Shell means like egg. Okay, only thing inside is hollow, nothing is there, only the thick covering is there, right? So if you just make a small hole and take everything out of an egg, then it becomes a shell. Okay, those who play plastic ball, okay, plastic ball, yes, cricket ball, so the plastic ball can also be considered as a shell, because inside the plastic ball nothing is there, so only outer hard covering is there, inside it is hollow, so that is called a shell. Okay, outside the shell, electric field is basically 1 by 4 pi epsilon naught Q by r square, same as the charge, point charge capital Q. Only thing we consider that entire charge is located at the center of the shell. Okay, and electric field is basically proportional to 1 upon r square, similar to that of point charge, but there is one catch, that inside the shell electric field is 0. So inside the shell electric field is 0. So it obeys the normal formula for electric field only outside the shell, but inside the shell electric field is 0. Okay, so that is the only exception to the normal case. And if you plot the graph looks like this. This is 1 upon r square graph, but for normal charge it actually start exactly from 0, but for shell there is nothing up to r is equal to capital R. So up to this point electric field is 0, it suddenly starts at this point. So this is a discontinuous point. Up to this point it is 0, suddenly it is increasing, and then it is decreasing again, right? Now next chapter, electrostatic potential and capacitance. So in electrostatic potential we learned about the work done to move a charge, right? So to calculate work done in general we have to use this formula, external force that we have applied times a small displacement, and then integrate it from starting to final position. Okay, in terms of potential energy, it is given by the final potential minus initial potential. Okay, you can write this as final minus initial. Okay, and this also from the conservation of energy, this has to be the work done on the system. So either you can calculate work done using the force formula, or you can calculate the work done by finding the difference in potential energy. Now potential due to a point charge. Potential due to a point charge is given by 1 by 4 pi epsilon naught Q by R. 1 by 4 pi epsilon naught q by r. The potential due to an electric dipole is given by V is equal to 1 by epsilon naught P cos theta by r square. So as you can see, in case of electric field normally varies as 1 upon r square, but due to a dipole it varies as 1 upon r cube. Similarly, potential normally varies as 1 by r, but for dipole it varies as 1 upon r square. So proportional to 1 upon r square. Now potential is a scalar quantity, right? Potential energy is also scalar quantity, work done is also scalar quantity, and electric potential is also a scalar quantity. Electric field is a vector quantity. Capacitance of parallel plate capacitor. Before going into that, I just want to add one more basic formula, which is the relationship between electric field and potential. Generally it is given by minus dV by dx. Okay, so this is the relationship between electric field and electric potential, and it is very handy to calculate. Sometimes they will give you a case where distance is known, potential difference is known, and they asked you to find the electric field. That can be calculated using this formula. Now let's move on to the parallel plate capacitor, the next very important point of this chapter. So capacitance of a parallel plate capacitor is given by C is equal to Ka epsilon naught divided by D. Okay, K is the dielectric constant of the parallel plate capacitor. So if you have a parallel plate capacitor and if you have some medium within it of dielectric constant, say K, then the capacitance is given by this formula. Okay, normally if only air is there, then value of K is 1. Otherwise, K value whatever they will provide, so dielectric constant of medium 4, dielectric constant of the medium is 6. So that value you have to use in this. This is the general formula. Okay, in textbook mostly you will see A epsilon naught by D, but K is for dielectric medium. Now energy stored in a capacitor is given by half CV square, which is also equals to half Q square by C, which is also equals to half Q into V. Now the formulas that you will use will depend on the given value. So only suppose there is a question where Q and C are given and they asked you to find the energy stored. Okay, so that will be the formula you have to use. Now energy generally stored in form of electric field. Energy in a capacitor, parallel plate capacitor, is stored in the electric field. So if you calculate the energy density, it will give you the relationship between the electric field and the energy density. Okay, so you have to remember that energy in a parallel plate capacitor is stored in the form of electric field. Okay, so electric field means conservative force field. So if you do some work against it, it will get back that work. That's how you get the energy. Now in series combination of capacitor is 1 by C Q is equal to 1 by C1 plus 1 by C2 and so forth and so on. If only two capacitors are involved, then C equivalent becomes C1 plus C2 by C1 into C2 divided by C1 plus C2. Right, only two capacitors are involved, so then this is the formula. And if n number of capacitors of same capacitance are connected in parallel, then what would be the effective capacitance? Mention that in the comment below. Easy question. Suppose we have n number of capacitor each having same capacitance of C. We have n number of capacitor each having same capacitance C connected in series. What will be the equivalent capacitance for this particular system? Mention that in the comment below. Now in parallel combination, capacitance generally gets added. Now one more thing, in series combination, the charge passing through each capacitor remains the same because it has no other path to flow. So whatever charge is passing through the first capacitor, same charge will pass through the second capacitor and third capacitor and fourth and so forth and so on. So charge passing through each capacitor remains the same. In parallel combination, voltage across each capacitor remains same. So in parallel combination, voltage across each capacitor remains same. Okay, voltage across each capacitor remains same. Okay, and In case of capacitance, capacitance simply gets added. Now student sometimes get confused between series and parallel combination of resistors and capacitance, because obviously in parallel combination of resistors we see 1 by R is equal to 1 by R1 plus 1 by R2, and in case of series combination of resistances it gets added. But in case of capacitor, the combination sequence is opposite, right? In case of series it is getting added inversely, whereas for parallel they are just simply gets added. So be careful, little bit extra careful initial days. Once you have practiced enough questions, you will not have this confusion. Next is current electricity chapter. Now let's look into current electricity. So first is definition of electric current. So electric current is defined as charge divided by the time, right? Charge divided by the time. Now there is a general definition, which is basically if you take the time delta t and take it towards 0, then delta q by delta t gives you the current, and in differential definition it is dq by dt. This is more accurate answer because if the current is not steady, then this formula is applicable. If the current is steady, that is constant over time, then you can use this formula. Now Ohm's law, the most important law, normally the form is V is equal to IR, R is called resistance, but there is an alternative form of Ohm's law, J equals to sigma into E. Here sigma is called conductivity. Okay, sigma is called conductivity. Energy that is dissipated in a resistor is given by VIT, vitamin, right? There are other forms as well, I square RT, V square by R into T. So these are all other forms of the same formula. So energy dissipated in a circuit is basically vitamin. Energy is vitamin. If you eat vitamin, you will get energy, right? So H equals to VIT. H means heat energy basically. Okay, so heat energy is vitamin. Okay, remember this way, you will remember forever. Next is power. Power is the power dissipated in unit time. So if you divide H by T, you will get power, which is nothing but Vodafone Idea. Power is Vodafone Idea. Okay, just to remember it, nothing to do with the companies. VI, P is equal to V into I. Also can be written as I square R or V square by R. Based on the question, based on the problem, based on the given values, you can use different combinations. Now let us look into drift velocity. Drift velocity is what is drift velocity first of all? So normally if you consider a conductor means a piece of iron, any piece of iron. Okay, even the pen that I am holding is a metallic pen. Any conductor, okay, any conductor, they have a lot of free electrons. Okay, and those electrons basically moving randomly. Normal cases, all the electrons present in a conductor, they move randomly because electrons are generally free, right? So those free electrons, they cannot leave the surface of the conductor, but they can move freely within the surface of the conductor, right? So suppose you are alone at home, your parents have gone outside, they have locked you from inside outside, so you are not allowed to go outside. They asked you to go and study for your upcoming exam, but what you are doing, okay, parents are not at home, I will play cricket in my bedroom. Okay, so you are throwing the ball and playing the cricket. So don't try to do that, it will break your furnitures and your parents will scold you. But so this is how you are, I can explain you to the situation of an electron. So parents are not at home, so electrons can move around within the conductor for free. Okay, now what will happen if you apply an external electric field around it? What will happen if you apply an external electric field around the conductor? Now your home tutor came to your home to teach you. Okay, and what is happening to you? You are seeing the teacher and you are moving in the opposite direction. Sir, please don't teach me. Please don't teach me. Or in the college, suppose the teacher who is scolding you, you say, sir, please don't say anything. Please, sir, forgive me. I made a mistake. So that's what happened. The electrons starts to move slowly in the opposite direction of the applied electric field. Okay, so this is how the electrons move inside a conductor. They slowly moves opposite to the electric field, and they have this random motion is still present. The random motion is still present in the electrons, but they also have a aggregated total velocity in the opposite direction of the electric field. That is called as drift velocity. Electrons are drifting. Okay, they are drifting. For example, if you ever visited a seaside or a lakeside, okay, if you throw something in the water, normally the water will bounce up and down. Right, normally, for example, if you throw a ball in a lake, normally the ball will just go up and down with the tide. But if there is a wind blowing, okay, wind blowing, and there is a small wave inside in the lake, then the ball will slowly start drifting in the direction of the wind. Right, so that is what is called drifting. The term came from this idea of drifting, means if you leave something and allow it to move automatically, then it starts moving in a particular direction. That is called drifting. So the drift velocity is given by charge of an electron into electric field that you have applied divided by mass of the electron times the relaxation time. What is the meaning of relaxation time? Relaxation time means when the two electrons collide, or electron and another atom collide between them. Okay, so there is a time interval between two consecutive collision. So first collision suppose happens over here, second collision suppose it happens over here. So there is a time gap between two consecutive collisions. Okay, suppose this time is t1, this much time is t2. Now if you take the average of all such collisions, then whatever you get, that is called the relaxation time tau. Now this is not the calculation is not that easy. Okay, the relaxation time is a statistical quantity, so those who have statistics perhaps will understand. You have to take a lot of samples and then add them and then divide it, right? So that is a very long mathematical process, okay, highly mathematical process. But the definition of relaxation time is that the time difference between consecutive collisions, if you take the average of that, that will give you the relaxation time. Now the current, because of this drifting of electrons, there will also be a current present in the circuit, right? So if you apply an electric field, there will be a current flowing in the circuit as well, and generally current is considered to be in the direction of electric field. So electric field means what? You have applied a battery. Okay, if you apply a battery, then there will be definitely a electric current which will pass through the conductor, and that current expression is given by I equals to NEA VD. Very important, very important formula for your PU board, for your KCET, for your JEE, for your NEET, whatever exam you are preparing. I is equal to NEA VD is the one of the most important formula, especially for KCET. So yes, there, but for all other examination as well, this is a very important formula. Now what is N? N is number density of electrons. Number density means what? If you take 1 meter cube of the sample, 1 meter cube means 1 meter length, 1 meter height, 1 meter breadth. So if you take that much of material, for example, if you are considering iron, you take 1 meter iron, 1 meter length, 1 meter height, 1 meter depth, then whatever is the number of electron present in that volume, free electrons, whatever is the number of free electron present in that volume is called the number density of electrons. This is the number density of electrons, number of electron present per unit volume. So that is what N. E is charge of an electron, A is the area of the conductor, okay, and VD is the drift velocity. Now from this relation, one more thing I want to tell you, that the current when it starts to flow, it remains constant even if you change the cross sectional area. Okay, even if you change the cross sectional area, the current in the circuit will remain the same. Okay, but the drift velocity will change. Suppose this is VD1, this is area A, suppose this is VD2, this is area B. Then like equation of continuity that you have studied in class 11th, VD1A equals to B into VD2. So the drift velocity will adjust itself based on the surface area. Higher the surface area, smaller is drift velocity. Okay, smaller the surface area, higher is the drift velocity. Now there is one more important term which is called current density. We have seen in Ohm's law, alternative form of Ohm's law, J is equal to sigma E, right? So from there we can see that current density is basically given by I by A. Okay, current density is given by I by A. Okay, and if you put that value over here, you get this as NEVD. NEVD. Now if you put the value of VD over here, only the magnitude of VD over here, you will get this as NE square by M E into tau. Okay, NE square by M E into tau. Okay, and also the alternative form of Ohm's law is basically epsilon E. So what is this epsilon, by the way? Epsilon is conductivity. So conductivity is basically NE square tau by M. Okay, if you compare these two equations, you get the conductivity is NE square tau by M. Conductivity is also opposite to that of resistivity. We will come to the resistivity in a while. Okay, conductivity is also opposite to that of the resistivity. Also it is the ratio of J by E. Now mobility is how easily an electron can move inside the conductor, right? So that is defined by ratio of drift velocity and electric field. Ratio of drift velocity and electric field is the mobility of electron, and it is given by E tau by M. E tau by M. If you divide BD by E, you get E tau by M. So all these formulas are also important. Okay. Now resistance. This is something old that we are learning from class 10th. So resistance is directly proportional to length of the wire. Radius is directly proportional to length of the wire. Longer the wire, more is resistance. Resistance is inversely proportional to the area of the wire. Okay, so bigger the surface area, smaller is the resistance. Smaller the surface area, bigger is the resistance. And if you combine these two proportional relation, you have to use a proportionality constant which is called rho. So R is equal to rho L by A. What is rho? Rho is called resistivity of the conductor. Rho is called resistivity of the conductor. Now resistivity of a conductor depends on two things, only two things: material of the conductor and temperature. Material means iron, cobalt, copper, nickel, whatever you are using, that material and the temperature of the surrounding. Now if you are using a particular conductor, for example only you are using copper, okay, and you want to measure how the resistivity of copper changes with temperature. So resistivity of copper, resistivity of any material can be written as rho T. Resistivity at a temperature T is given by rho naught 1 plus alpha into T minus T naught. Okay, this is the general formula how resistivity varies with time. There are with temperature. There are few substances whose resistivity is almost constant because their this is called coefficient of resistivity alpha. Coefficient of resistivity alpha. Okay, some material has a very small alpha. Okay, very small alpha means even if you change the temperature by a huge margin, the resistivity remains same. One of such material is called nichrome. One of such material is called nichrome, and that is why it is used as a standard resistor. Okay, the resistance boxes. If you see, if you have performed any resistance related lab experiment in your laboratory, physics laboratory, you might have seen resistance boxes. Now resistance boxes use those materials which have very low coefficient of temperature of resistivity. For example, nichrome. Okay, if you plot the graph of temperature versus resistivity, for normal conductor it increases, okay, for nichrome it is almost constant, and there are few materials whose resistivity decreases. Okay, this is normal conductor. Some alloy, for example nichrome. nitromanganine, they are the example. And these materials whose resistivity decreases with temperature, they are called semiconductors. Okay, semiconductors are not proper conductors, they are very weird, they do not obey Ohm's law, okay, and their resistance decreases with increase in temperature. There is a dedicated chapter about these semiconductors we will study in a future lecture when we are discussing about semiconductors. Now, combination of resistance, we have already learned about combination of capacitance. Now let us learn about combination of resistance. In series combination, they simply gets added. Now the question remains same, what will be the series total resistance if you add n number of resistances in series, same resistance, n number of resistances in series of R, what will be the combined resistance? Mention that in the comment below. Now in parallel combination, again it is opposite, as I told you before, 1 by R equivalent is 1 by R1 plus 1 by R2 plus so 4 and so on. For two resistances, it will be R equivalent directly can be calculated R1 R2 by R1 plus R2. Okay. Similarly, we have combination of electric cells as well. There are two types of cells combination. Now, what is the meaning of cell? Cell means normally the cell that we say, they do not have any internal resistance, ideal cell. But in practical, not all cells are ideal cell. They do have some internal resistance. Okay, this internal resistance, if you cannot ignore when you are calculating something very, very specific, right? So for that, this is called the cell. This is an example of single cell. Now if you combine such cells in series, the total equivalent EMF of the cell is given by epsilon 1 plus epsilon 2 plus epsilon 3, so forth and so on. So in series combinations, EMFs gets added. Also the equivalent resistances also gets added. Now here we have assumed everything like plus minus like that, it is connected. Okay, it is connected like this. So if it is like this, then only you can add all of them. But if one of them is inverted, suppose you take this battery and reversed it, then there will be a negative sign in the EMF, but resistance will always be added. Resistance do not get negative, resistances cannot be negative, but if EMFs can be negative based on the orientation of the battery. Now in case of cells in parallel, this is the easiest way to remember the formula, that's what I have found. Okay, in cells in parallel, the equivalent EMF is epsilon 1 by R1 plus epsilon 2 by R2 plus epsilon 3 by R3 divided by 1 by R1 plus 1 by R2 plus 1 by R3. Okay, this is how you can calculate the equivalent EMF. And equivalent resistance is basically same as parallel combination of resistances. Now current through a combination of cell at any point is always given by epsilon equivalent divided by R plus Req. So total resistance, and this is the total EMF. Total EMF divided by total resistance. Here R is the external resistance connected in the circuit. Okay. Now let's move on to the next chapter, moving charges and magnetism. So moving charges and magnetism, here we have Lorentz force. Lorentz force is when a charge moves in an electric as well as magnetic field, presence of electric and magnetic field. So the force is Q into E vector plus V cross B vector. Okay. Also remember that a magnetic force acts on a charge when it is moving. If it is stationary, there will be no force acting due to magnetic field. Also, the velocity and magnetic field cannot be parallel. That means if velocity and magnetic field are in the same direction or in the opposite direction, V cross B will be 0, because V cross B means VB sin theta, right? Now if they are in the opposite direction or in the same direction, theta becomes 0 or 180 degree. So in that case sin theta becomes 0. But if they are perpendicular, the most common case that we consider is when V and B are perpendicular. So if V and B are perpendicular to each other, then it is simply sin theta becomes 1. So we generally consider that case only, and in that case the charge in the magnetic field, they rotate in a circular orbit. Okay, that circular orbit is very, very important to calculate the radius of that circular orbit, which is given by mv by qb. Okay, so if you have seen my lectures where I was solving questions, this formula came very, very often, right? So R equals to mv by qb. Angular frequency, so if it is rotating in a rotational motion, it will also have an angular frequency. The angular frequency is given by qb by m. Time taken for one revolution is given by t equals to 2 pi by omega. Okay, or you can calculate, it will be 2 pi m by qb. We solved one question based on this formula in our last lecture, right? Now Biot-Savart's law is also very, very important, as well as Ampere's law. They are basically cousin brothers, related to each other. So now when we are considering Biot-Savart's law, it states that magnetic field due to a current carrying wire, current carrying element, basically element means small portion of the current carrying wire, if you take it, and due to this element, what will be the magnetic field at some distance p from the wire. So it says that the magnetic field is directly proportional to the current I. It is directly proportional to the length of the element that you are considering. It is inversely proportional to the square of the distance. Okay, it is directly proportional to the angle sine it makes with the direction of the current element and the direction vector of the point. Okay, so you can write this as dPb is equal to mu naught by 4 pi I dl sine theta by r square. Okay, now here this mu naught by 4 pi is a proportionality constant, and its value is 10 to the power of minus 7 Tesla meter per ampere. Very, very important. Okay, sometimes we will use only mu naught. Mu naught is called permeability of free space. Epsilon naught was permittivity, here it is permeability. Okay, and mu naught we write it as 4 pi into 10 to the power of minus 7. Okay, SI unit. What is the SI unit? It is this, Tesla meter per ampere. 4 pi into 10 to the power of minus 7, very important value to remember to solve questions. And Ampere circuit law is basically same thing, but it is little bit more symmetrical. Okay, if the system is little bit more symmetrical, you can apply Ampere circuit law easily, which states that if you consider any closed loop around some current carrying wire, okay, in case it is symmetrical or proper way, you can calculate the integration. Otherwise the law is still valid for this case as well, but to calculate the integration it will be slightly difficult. That's it. Okay, so the integration will be complicated. It is not an integration based formula. This is normally a non-integration based formula. This is an integration based formula. For integration, we have to have a proper surface, similar to that of Gauss's law. If the surface is regular in that case or symmetrical, we could have applied Gauss's law. Here the line integral, because it is called line integral. Okay, because it's a curve. Okay, so if this curve is symmetrical and the system is symmetrical, it is easier for us to apply Ampere's law. That's it. So B dot dl equals to mu naught I. Okay, B is the magnetic field, dl is the line element of the curve that we are considering. Here dl is the current element, here dl is the line element. That is the difference between these two laws. Okay, and mu naught is obviously the free space permeability, and I is called the current enclosed by the curve. I is the current enclosed by the curve, similar to that of Gauss's law. In Gauss's law it was charge, in case of Ampere's law it is the current. Now force on a current carrying conductor. So if you keep a current carrying conductor in an external magnetic field, okay, it will experience a force. Okay, what is the value of the force? The force vectorially it is given by I into L cross B. I into L cross B. whereas mathematically normal magnitude wise it is given as F is equal to BIL sin theta, BIL sin theta. Remember that it is L cross B, and while writing it we write BIL. To remember it better, BIL is something which is seems like a name, okay, so that's why we write it as BIL sin theta. Next is magnetic field due to a straight conductor. Magnetic field due to a straight conductor. So we have a straight very long conductor and we want to find the magnetic field due to this current carrying conductor, means current carrying conductor obviously. Okay, so there is a current carrying conductor, current is passing through this is I, then what will be the magnetic field at this point P? So if the wire is finite, so it makes some angle theta 1 and theta 2 if you join the point and the top position and bottom position, okay, then theta 2 and theta 1 are the two angles that it makes. Then the magnetic field is given by mu naught I by 4 pi r times sin theta 1 plus sin theta 2. Okay, but if the wire is infinite, if the wire is very long, infinite wire, so in that case if you see, the theta 1 will go to pi by 2, theta 2 will also go to pi by 2. Okay, so that means this is 1, this is also 1, so 1 plus 1 will be 2. So for infinite long wire the magnetic field is given by mu naught by 2 pi I by r. So one of the two will be cancelled and you will have mu naught by 2 pi I by r. This is the formula for a infinite long wire. The same thing can be proven using Ampere's circuital law as well. Now circular current loop, this is one of the most common topic for PU board as well as KCET students. For PU board the derivation is very important. So we have a circular coil of say radius capital R, and we are trying to find magnetic field at some point P at a distance x from the center. So in that case the magnetic field is given by B is equal to mu naught I r square divided by 2 into x square plus r square to the power 3 by 2. This is one of the most commonly asked formula in entire KCET. So don't miss out this formula, try to memorize it as much as possible. Next, for center case, so if you shift this point to the center, so what will be the magnetic field? In that case x will be 0, because for center position x is 0. So if you move this point over here, x will become 0. That means it will be mu naught I by 2r. So at the center x equals to 0, so the magnetic field is mu naught I by 2r. For any points greater than 2r, for any point which is very farther away from the point, further away from the current carrying wire, you can simplify this and you will you can write this entire expression to be mu naught by 4 pi 2m by x cube. Here m is called dipole moment, I into a is m, and it is basically the dipole moment of the current carrying coil. It is magnetic dipole moment, not electric dipole moment, magnetic dipole moment. And if you can see that this expression is similar to that of the electric field due to a dipole on its axis, right? So this is similar to that of electric dipole on its axis. So we can say that a current carrying loop can behave as a magnetic dipole. So current carrying loop will behave as a magnetic dipole. In fact, if it carries a current in this direction, it will be a south pole, and if it is carrying a current in the anti-clockwise direction, it will be a north pole. You can remember the direction by just engaging the tail of the N or S, by extending the tail of N or S. Okay, so if you look it from top, and if you see that the current is flowing in the anti-clockwise direction, then it will be a north pole, and if you see the current is flowing in the clockwise direction, it will be a south pole. Force between two parallel currents, we have two parallel currents. Suppose distance between them is d, okay, IA, IB, okay, then the force between them is basically given by mu naught N IA IB by d, okay, into L. Here N may be if there are more number of wires are there, suppose one of them is carrying more current, that's why this N is. Otherwise I don't think this N is very important, so I don't want to keep that over here. I will remove it. I will remove this N. Okay, for a loop it is fine, but for straight wire I don't think N is fine. So mu naught Ia Ib by D into L is the formula for force between two parallel current carrying wire. There will be a 2 pi. Now force per unit length is when you divide this force by this capital L. Okay, so you have to take some arbitrary distance initially to calculate the force, and then you have to divide the force with this length to calculate the force per unit length. Okay, so this is the formula for force per unit length. Now you also have to remember that current in the same direction they attract each other. Current in the same direction they attract each other, whereas current in the opposite direction they repel each other. If the current is in the opposite direction, they repel each other. Okay, same directional current attract each other, opposite directional current repel each other. Now torque on a rectangular current loop. Torque on a rectangular current loop. So if you keep a current carrying loop in an external magnetic field, so the loop is also behaving as a magnet. There is also external magnetic field present over here. So what will happen, you can consider this to be the case where electric dipole placed in a external electric field. Similar to that, what was that expression? There was a torque acting on the electric dipole. Similarly, if you keep a magnetic dipole in an external magnetic field, it will also experience a torque. So here we have a current carrying loop which is equivalent to an magnetic dipole. So this magnetic dipole will experience a torque, and the value for this torque is m cross b. Scalar wise it will be mb sin theta. Okay, and m is given by NIA, National Investigative Agency. Okay, because n number of turns are there, that's why NIA. If only single loop is there, it will be only IA. Now you can convert a galvanometer into ammeter or into a voltmeter. Okay, there are different ways to do it. You can, the problems you have to practice it on your own. I have solved a lot of questions on this conversion. That there is something you have to remember formula wise, which is current sensitivity and voltage sensitivity. So how good a ammeter is, that determined by the current sensitivity of the ammeter. Now to calculate that, we are using phi by I. Phi is number of division divided by current I. Mathematically it is given by NAB by K. Okay, NAB by K. So if you increase the number of turns N, AB is the part which is area of the loop, right? So K is the spring constant, B is the length, distance between the two arms, right? Now N, if you increase the number of turns N, current sensitivity also increases, right? If you increase the number of turns N, current sensitivity also increases. Now voltage sensitivity of a voltmeter is given by NAB divided by RK. R is the resistance of the coil. Resistance of the coil. Now if you increase the number of turns, what is happening? More number of turns means longer the wire, total length of the wire increases. So the resistance is directly proportional to number of turns. Okay, resistance is directly proportional to number of turns. More number of turns means more resistance. So that is why by only increasing the number of turns, the voltage sensitivity will not change. Voltage sensitivity is independent of the number of turns. Okay, whereas current sensitivity directly proportional to number of turns. So there was one question where it was asked, if you increase the number of turns, the voltage sensitivity will increase or current sensitivity will increase. Only current sensitivity will increase, voltage sensitivity will remain the same. Now let us move on to the next chapter, ray optics. So now let us look into the ray optics equation. So all the difficult calculations related formulas are almost done. Now slightly mathematical, but you have practiced. Ray optics are easy. Wave optics, again we will see a little bit more some tricky more equations. So spherical mirrors, mirror equation is 1 by V plus 1 by U is equal to 1 by F, or 2 by R. R is the radius of curvature of the surface. Now magnification is given by M equals to minus V by U. So remember that magnification of spherical mirrors is minus V by U. There is a negative sign. Okay, refractive index is the inversely proportional to the wavelength of the light. So n is 1 upon lambda. N is proportional to 1 upon lambda. So refractive index is basically when light enters from one medium to another, how much the light will bend, whether it will bend towards the normal or it will bend away from the normal, that is determined by this refractive index, right? So that refractive index is inversely proportional to the lambda. So higher the wavelength, okay, the bending is smaller. Higher the wavelength, the bending is smaller. For example, if red light enters from air to water, it will bend less compared to a violet light. Violet light will bend more. Okay, so refractive index for violet is more compared to red. So based on this very simple concept, more than 3-4 questions have come in the past. So just remember this very simple fact, and you might find one question which is coming based on this very easy concept. Now absolute refractive index, this is an optional calculation. Okay, so absolute refractive index is basically the speed of light in a particular medium divided by the velocity, speed of light in free space. My mistake. C is 3 into 10 to the power of 8. Speed of light in free space divided by speed of light in a particular medium. Okay, so this is the refractive index, absolute refractive index of any medium. Now absolute refractive index of any medium is generally cannot be less than 1. Absolute refractive index cannot be less than 1. Minimum value of absolute refractive index is 1. Minimum value of absolute refractive index is 1, and the medium is either you can say vacuum or you can say air. Okay, air and vacuum have the same refractive index, which is 1. Relative refractive index can be less than 1, but because relative refractive index depends on the ray of light which is traveling from which media to what media. For example, relative refractive index of air with respect to water can be less than 1. Cannot be negative, but it can be less than 1. Okay, that is a small derivation. So refractive index can be converted into square root of mu r epsilon r. This derivation is not super important for your KCET preparation, but if you are preparing for a Comet K, I have seen a few questions coming from this formula. And relative refractive index is speed of light or speed of light in the first medium divided by speed of light in the second medium. Suppose the light is traveling from medium 1 to medium 2. Okay, this is medium 1, this is medium 2. So light is traveling. Now refractive index of the second medium with respect to first medium. Refractive index of the second medium with respect to first medium is given by N21 equals to V1 by V2. It is also can be written as absolute refractive index of the second medium divided by absolute refractive index of the first medium. Okay, so this is in terms of absolute refractive index, this is in terms of speed. Next is refraction at a spherical surface. So refraction at a spherical surface, so when light is traveling, suppose this is a completely some glass medium, light is traveling from air to a particular medium, then what will happen? Okay, so for that you have to remember that generally the image is being formed in the second medium. So this is V, this is U, and the refractive index of this medium is N2, refractive index of this medium is N1, the radius of curvature is R. Then this is the formula you have to remember: N2 by V minus N1 by U equals to N2 minus N1 by R. Okay, so V is in the second medium, so N2 by V. U is in the first medium, so N1 by U. So N2 by V minus N1 by U equals to N2 minus N1 by R. Okay. Apart from that, there is also a lens maker's formula. Lens maker formula is applicable for lenses and in any spherical surfaces. Focal length of any curved surface is given by N21 minus 1 times 1 by R1 minus 1 by R2. Okay. So here, suppose we have a lens. The radius of curvature for the first surface is R1, radius of curvature for the second surface is R2. Then this is the formula. Here N21 is the refractive index of the medium of the lens with respect to the surrounding. N21 means refractive index of this medium with respect to the surrounding. In case it is air, then you can take absolute refractive index. In case it is not air, suppose it is water, then you have to divide with the refractive index of the water. Lens equations. So 1 by V minus 1 by U equals to 1 by F, easy. Magnification of lens, it is positive V by U. Now remember that whenever you are applying these formulas, be it mirror, be it lens equation, be it lens maker's formula, sign convention is very, very important. And sign convention is that we follow Cartesian sign convention. Anything along the positive x-axis is positive, anything along the negative x-axis is negative, anything in the positive y-axis is positive, anything is negative y-axis is negative. So this is how we measure the distances. Generally lens, mirror, etc. is placed at the origin. Mirror, lens, etc. are placed at the origin. The object is generally placed on the left hand side of the object, so object distance will always be negative. Object distance will always be negative. Okay, so U is always negative. If V is negative, then object and image are on the same side. If V is positive, then object and image are on the opposite side. This is the basic case. Now based on mirror and lenses, these two can give you different cases of virtual and real images, but this is the very, very basic sign convention. Okay. Now power is given by 1 upon focal length. Now here very, very careful that this focal length is measured in meter. This focal length is measured in meters. In case you are measuring focal length in centimeter, then the power becomes 100 by F, where F is in centimeters. Most commonly in 90% of cases you will see that the focal length is given in terms of centimeter. So you can use this formula. Now lens combination, when two lenses of small very thin aperture, the thickness is very thin, okay, then the combined focal length of two lenses in contact is given by 1 upon f1 plus 1 upon f2. Okay, P equals to P1 plus P2. Power will be added. Now refraction through a prism. So when a light ray passes through a prism, okay, it suffers something called a deviation, okay, angle of deviation. So the ray deviates from its original path. This was its original path and it deviates to a different direction. The angle between the original path and the final direction is called deviation, and the angle corresponding angle is called angle of deviation. So general formula for angle of deviation is given by delta equals to I plus E minus A. I is angle of incidence, I is the angle of incidence, and E is the angle of emergence. Now for it can be shown, we have done the derivation that a particular angle when this I and E becomes equal, the angle of deviation becomes minimum. The angle of deviation becomes minimum only when I and E are equal. So that is the particular case which is called angle of minimum deviation, and correspondingly you can calculate that particular incident angle, which is given by A plus delta M by 2. A is the angle of prism. A is the angle of prism, that is the angle of the apex angle. This is the apex angle. Okay, so this is called angle of the prism. Okay, so this is how you can calculate the angle of incidence. Now corresponding refractive angles, say R1 and R2, normally can be related to the angle of prism is by R1 plus R2 equals to A. Okay, R1 plus R2 equals to A, and for minimum deviation, obviously R1 and R2 will also be equal, I and E are equal, so R1 and R2 will also be equal. So that value R1 equals to R2 equals to R will give you the minimum angle of deviation, and from there you can write angle of refraction is given by A by 2. What is refractive index then? Refractive index is sin I by sin R from Snell's law. So from there you can find the refractive index of the material of the prism, refractive index of the material of the prism. Now optical instrument, we have two optical instruments, microscope and telescopes. The magnification for microscope is given by L by F naught times D by Fe, whereas for telescope it is given as F naught by Fe. In case of telescope, the total length is also Fo plus Fe, right? For microscope that is not the case, but for telescope lengths of focal lengths must be added so that it is perfectly fitted. Refractive telescopes have zero chromatic aberration. Refractive telescope means not refractive, reflective. This is wrong. Reflective telescopes have zero chromatic aberration. That means we know that when light refracts, the refractive index changes with the color, right? It depends on lambda. So each color bends at a different angle, so that different bending gives rise to a completely disfigured, discolored image, which is called chromatic aberration. Chromatic aberration can be corrected using different ways. For example, currently the video that you are watching is recorded through a lens. Okay, the lens, it is by nature the lens will change the colors to different angles, but the lens, the camera lens has a technology which can correct this error. Okay, but for a light which is very high, so for example, that's why when we record we use a lot of lights. You may have seen during different recordings or movie shootings, they use a very huge amount of light. Why? Because so that the camera can recognize all different colors and eliminate the chromatic aberration. Okay, but for a star, when you are observing a distant object, very distant object, okay, for a star with very few amount of light is coming, okay, so in that case it is very difficult for us to eliminate the chromatic aberration. There are ways, no problem in that, but if you are using reflective telescopes, okay, they do not possess any chromatic aberration. In case of reflection, angle of reflection does not change based on color. All colors are reflected equally. Okay, so that's why reflective telescopes are preferred over refractive telescopes when you are observing a very sensitive long distance stars or galaxy. Now let's move on to the last chapter, wave optics. So interference of light. So when light, say two displacements y1 and y2, they meet at some point, okay, the resultant wave will have a amplitude of a1 square plus a2 square plus 2a1 a2 cos phi. What is cos phi? Cos phi is the phase difference between these two overlapping waves. Now if this phase is constant with time, if phase at particular point is constant over time, then they are called coherent sources. If this phase is not constant over time, then they are called incoherent sources, and this resultant amplitude will change and you will see a average out value. You will not see this any change in the intensity, you will see some averaged out values, okay. But if the phase is constant, the amplitude at different location will remain will be same. So suppose the amplitude here is 10, here 5, here 4, here 3, so that will stay as it is, and you can detect how the amplitude is changing. The resultant intensity is given by I proportional to r square. Intensity is always proportional to amplitude square, so resultant intensity is given by r square, and if you put the corresponding values of this is as I1, this as I2, then this formula can be rewritten as intensity equals to I1 plus I2 plus 2 square root of I1 I2 cos phi. Now if both the light which is superposing at this point, they have the same intensity, then this resultant intensity can be written as 4 I naught cos square phi by 2. Now based on if the rays which are interfering, if they are coherent sources, based on the position, we observe two different types of intensity, okay, where in first case we observe intensity maximum, which is also called bright fringe, okay, or constructive interference. Okay, in case of constructive interference, the path difference is given by delta x equals to n lambda. Okay, n is an integer, and in terms of phase difference, it is given by 2n pi. Normal formula for phase difference is equals to 2 pi by lambda into delta x. So if you know path difference, you can convert it into phase difference as well. This is the conversion formula. Okay, position of the bright fringe is given by y is equal to n lambda d by small d. Okay, path difference for destructive interference. So in some places you will observe that the intensity decreases, right? Intensity is minimum. So in case intensity is minimum, they are called destructive interference or dark fringe. Okay, dark friend, not dark friend, fringe. So path difference is given by delta x equals to n minus half into lambda. Phase difference is given by phi is equal to 2n minus 1 into pi. Okay, position of the dark fringe is given by y equals to n minus half lambda d by d. Now suppose there is a bright fringe and then we have a dark fringe. We have a bright fringe, we have a dark fringe. Okay, bright fringe I am marking it like this. So this is bright, this is dark, bright, dark. So this is called fringe width. The width of any of the dark band is called fringe width. Now in case of interference, the width of the bright fringe and dark fringe are same, and that value is given by beta equals to lambda d by d. As you can see, it is independent of the order. For whatever order it is, the fringe width is always constant. It is given by lambda d by d. Now diffraction is when instead of two lights, when only one light is coming and it is allowed to bend at a single opening. Okay, if you allow the light to bend at a single opening, interestingly you observe that there is a central maxima and there is a darkness, then also there are secondary maximas as well. Normally what you expect is that when I switch on the torch, I expect the frontal ground to be illuminated, but instead only on the frontal ground some sides are also getting illuminated, which was very surprising. That phenomena is called diffraction. Okay. In case of diffraction, suppose you are observing a diffraction pattern. So this is the intensity maximum. Okay, then you are seeing some dark, then some bright. So the peak suggests some bright fringe. These are the bright fringe, these are the dark fringe, and this is the intensity of the light, and this is the width of the light. Okay, this is called angular width. This is called angular width, theta. This is the half angular width. This is half angular width, this is full angular width. Full angular width is 2 theta. Okay, the half angular width is given by lambda by a. What is a? A is the width of the slit. Slit means the opening, the width of the opening through which you are switching on the torch. Okay, so this is the width of the slit, and theta is given by lambda by a. The width of the central maxima, the total width is 2 theta. So basically 2 theta means it will be 2 lambda d by d. 2 lambda by a. This is angular width, so the distance does not matter. Okay, and for central maxima, it is a sin theta equals to n lambda. Generally n is 1 for central maxima, that's why a sin theta is equal to lambda for central maxima. Okay, so these are the very important formulas that you will remember. And last formula, last but not the least, one of the formulas which came repeatedly in KCET year after year, that is based on Malus law. Okay, Malus law says that when light of intensity, say I, light of intensity I passes through a polarizer, light of polarized light, obviously here I naught is the polarized light. Suppose we have a polarized light of intensity I naught passes through a polarizer and the angle is say theta, then the intensity of the emergent light is given by this formula. Intensity of the emergent light is given by this formula, I naught cos square theta. Okay, I naught cos square theta. Now in case any unpolarized light, this is polarized light. In case an unpolarized light is passed through a polarizer, it will also gets polarized. We have to remember this as well. So if a light of unpolarized light passes through a polarizer, it gets polarized. Okay, and that polarized light will have an intensity of half of the original light. Okay, UP means unpolarized light, P means polarized light. Okay, this is also very important, but very often people forget it. So this is also very important formula. Now with this I would like to end this lecture. It is slightly longer because we reviewed all the chapters that we have studied so far. I'll be back with very new videos very soon. Till then, bye.